We've covered the why. Now let's look at the what, the AI ML compute clusters that do the actual heavy lifting, and the models that run on them. Get a handle on clusters, custom versus pre-trained models, parameters, and placement, and you've got the foundation for every sizing decision you'll make across the rest of this course. When AI gets serious, you stop thinking in servers and start thinking in clusters. And this slide is the spine of the entire course. So let's give it real attention. Number one, an AI ML cluster is many GPU servers lashed together to act as one single scalable system. Look at the diagram. Node 1, Node 2, Node 3, all the way out to Node N, pooling their compute, memory, and storage. Number two, a training job gets partitioned and spread across all those GPUs and nodes, so every GPU stays busy. Number three, and here's the consequence that drives everything, that creates heavy east-west GPU to GPU traffic between nodes. Constant, high-volume data exchange, server to server, sideways across the fabric. Not the old north-south client-to-server pattern, sideways GPU to GPU. Which leads straight to number four. It demands a lossless, high-bandwidth, low-latency fabric. And I want you to really feel why. Look at those leaf and spine switches wiring the nodes together. If that fabric drops a single packet or adds latency, the GPUs stall, they sit idle, waiting on the network while the meter keeps running. You've got millions of dollars of GPUs twiddling their thumbs because a switch hiccuped. That's exactly why we'll obsess over lossless Ethernet, ROSI, and congestion control in the modules ahead. Every bit of it exists to keep those GPUs fed. Number five is the mindset shift. The cluster, not the single server, is the unit of design. You design the whole thing as one machine, compute, that leaf spine, network, shared storage for data sets and checkpoints, network services, and management and orchestration. Think of a rowing crew. It doesn't matter how strong each rower is if they're out of sync. The boat only flies when everyone pulls in perfect rhythm. Your cluster is that boat, and the lossless fabric is the rhythm keeping every GPU stroking in time. Burn that in. In the AI world, you feed the cluster as one organism, and everything in the network and fabric modules exists to make that happen. When it comes to the models themselves, you've basically got a menu, and the slide lays out 5 choices left to right. Number 1, pre-trained models, ready to use, fast to deploy. Someone else already paid the massive training bill, you just grab the model and run inference. Out of the box, fastest time to value, lower upfront cost. Number 2, custom models built and trained on your own data, highly tailored and powerful, but look at the trade-offs, costly in compute and talent, and far longer to stand up. Number 3 is the sweet spot most shops land on. Fine-tuning, start with a solid pre-trained model and adapt it with your data. Most of the benefit at a fraction of the cost. Number 4, model optimization, pruning and quantization to shrink the model and cut compute and cost. And number 5, frames the whole decision, build versus buy. Now drop to the bottom of the slide because this is the part that's actually yours. Build versus buy completely changes your infrastructure bill. Look at the buy. Pre-trained side, cloud and API access, internet connectivity, security and governance, monitoring, and notably lower upfront investment. Now the build, custom side, GPU compute capacity, high performance storage, high speed networking, MLOps, and a whole AI and ML team. That's a serious, expensive cluster. Exactly the kind of thing this course teaches you to design. So here's the lesson. The moment the business tells you which road they're on, you know what to provision. We're just calling a pre-trained models API means a relatively light footprint. We're training custom models on our proprietary data. Means stand up the GPU cluster, the lossless fabric, the fast storage, the works. Think of it like transportation again. Buying pre-trained is taking a rideshare. Quick, cheap, zero maintenance. Building custom is buying and running your own fleet. Total control, but now you own the garage, the mechanics, and the fuel bill. Neither is wrong. They're different strategies with very different infrastructure tabs. Read which one the business picked, and you'll provision right. Two concepts to lock in here, and the slide splits them cleanly down the middle. Left side, model parameters. Parameters are the model's learned weights, and the simple rule is right there. More parameters means bigger, smarter, heavier. And critically, parameter count drives GPU memory and compute needs. Look at that scale along the bottom. Small, under 1 billion parameters. Low memory, light compute. Medium, 1 to 10 billion. Large, 10 to 100 billion. Very large, 100 billion and up. Massive memory, massive compute. So when someone says a 70 billion parameter model, your brain should instantly translate that to, that's going to need a serious pile of GPU memory just to load. Parameters are your shorthand for how heavy the model is. Right side, service placement, where the model actually runs. And there are 3 homes. On premises, maximum control and security, keeps your data local for data gravity and compliance, predictable performance, ideal for sensitive, steady workloads. Cloud, elastic scale for demand spikes, pay as you go, global reach, perfect for bursty or experimental work. And distributed/edge, low latency, real-time inference right next to where the data is born with reduced bandwidth and better privacy. Most enterprises end up running a blend of all 3. Now connect the 2 halves because that's the whole point. See the bottom banner. Right model, right place, maximum impact. Parameters tell you how heavy the model is. Placement tells you where that weight should sit. A small, fine-tuned model doing real-time inference, push it out to the edge. A giant model you're training from scratch, that's your on-prem GPU cluster or cloud burst. Match the 2 and your size and decisions practically make themselves. Get sloppy, drop a heavy model in the wrong place, and you're either blowing the latency budget or the cost budget. The exam expects you to weigh both levers together, and so will every real design you ever touch. Master parameters and placement, and you're officially thinking like an architect.